talking about area under the curve and how it relates to what we've done before. So algebraically, we've done this kind of stuff, just simple rules of integration. If I did integration of sine x from 0 to 2 pi, u equals 0. Okay, visually, this is what we end up with, or algebraically, that's what we end up with, no matter which way you solve. So this emphasis will be on the understanding, the conception of this, or the ideas of this more than the algebra that goes on. I'm going to have some faith that you guys can do the algebra then. So if we talk about the area under the curve for sine of x from x equals 0, here's the idea. If we go sine of x dx, then every y value is coming from sine x, and every x value is coming from dx. So changing x's all the way across from 0 to pi goes that way, positive values. Changing y goes up this way, positive values. So if I integrate from 0 to pi and get the area of that, this equals 2. Now, if I go from pi to 2 pi, all the x's are positive values, but my y's end up negative values. So the area of this equals a negative 2. But we can't have negative area. It's the same way as when we talk about velocity. If I go backwards and I end up at 0, it doesn't mean I traveled 0 distance total. I can still add that up. So really the area of this should be 4. So the idea is I got to go from 0 to pi of sine x dx minus pi to 2 pi of sine x dx. And I only use the negative because I know this is a negative area and I got to flip that somehow. And there's a couple different ways I can do that algebraically. But I have to be aware of when I have positive area and when I have quote unquote negative area, because I need to find the total area under the curve, not what cancels out. So that does bring me up to the very first thing. If I find the area under the curve of this sine x, we can always use absolute values. Really, this only helps with calculators because it doesn't make it any easier algebraically by hand if I throw an absolute value. But if I actually write this graph as absolute value of sine x, then you notice everything's above the x-axis. So if I integrate that, I get my 4 a quicker way that way. So let's get into some of these other ones. So if I got the area of the curve that's bounded by y equals 2 over x plus 1, the x-axis, line x equals 0, and then line equals x equals 4. Graphing. If we're taking a look at it, what I've asked you to do is find the area bounded by the x-axis, x equals 0, x equals 4. Since none of it ever goes below the x-axis, this one's not too tough. I'm going from the bottom bound is from 0, the top bound is 4. I'm integrating 2 over x plus 1 in terms of dx. And I can integrate from here. Bring the 2 out, I end up with 2 natural log of x plus 1, absolute value, plus c from 4 to 0. So 2 natural log of 5. And then if I plug in 0, that's natural log of 1, which is 0, minus 0. That's it. So algebraically, it's not too tough. That is now the area under the curve between 4 and 0. Because it never goes below the x-axis, it never goes to negative area, I can just do it that way. Quickly, finished, done. So let's make it a little more complicated. Give you something like this. I want to find the area under the curve of 8 minus x cubed, the y-axis, and the x-axis. Now, I've had people make this mistake where they say, well, here's the y-axis, it keeps going. Here's the x-axis, it keeps going. And this function keeps on going. So why am I not finding the area of this? The answer is it's not bounded. It's not closed. It's infinity. There's no way of getting any of those answers if it's not bounded. It keeps going down forever. So you do have to think what's actually bounded by that. It means we were finding all of this. And anytime we find the area of this, I'm actually finding the area to the x-axis, and the x-axis only. So that's everything because it's dx and it's the y value. So this one ends up being the integral of 8 minus x cubed in terms of x. The first part's pretty easy. I just figure out where this is, and that's at 0. That's the y-axis. The top part, I got to go 8 minus x cubed. When does it equal 0? And I'm trying to find that point right there. Solve that, I get 2. I can solve from there. Okay? Whichever way you want to do it, I'm not going to go through the steps on this one because you guys can figure that out. But this is going to equal the area under the curve, bounded. Curve. And this will be key for the x-axis. All right, mixing it up a little bit. Find the area of the region bounded by the graphs of 2 minus x squared, gx equals x, and the y-axis. They want to find this. Now, if I integrate, and I'll do this with colors off of this. Oh, might be a little misleading. If I integrate, or find this, let's do this first. Let's find the intersection of both of these, because this hits at x equals 1. Okay? If I integrate from 0 to 1 of f of x, what I've ended up getting is this area right here, including, because it goes all the way down to the x-axis. So this represents that area right there. Integral from 0 to 1 of the f of x. That's not what I want, though. What I want is just the area here. So I need to subtract the area from 0 to 1 and realize if I'm cutting it off at 1, none of this has to deal with it, of g of x. Because if I do subtract this area, I'm in essence subtracting, whoa, too much. This area here. I'm subtracting everything that's under y equals x to this point, left with that. So this would end up giving me the area that's bounded by 2 minus x squared, x, and the y-axis. Okay, let's try a little bit different. And like I said, I'm really focusing on the conceptual part. I've changed the functions around a little bit. So f of x, 4 minus x squared. So this is f of x. G of x, I dropped it 1 just so you can see it, and the y-axis. So I'm going to label stuff as A, B, but I'm going to draw a line here at 1.79, and C. Okay? A, B, and C represent the areas of those specific. So A is all of this area. B is this triangle. And C is this triangle. So it represents all of those ones. So if I get the integral, now realize my goal on this one is to find this area here, bounded by f of x, g of x, and the y-axis. That's my goal. So if I integrate from 0 to 1.79, by the way I got 1.79 is set those two equal to each other. Find this intersection here. If I integrate from 0 to 1.79 of f of x, I get something interesting. I get the area of A plus, well, area of A plus B, because realize if I integrate from 0 to 1.79 of f of x, it gets everything that's contained by that to the x-axis. So it's all of that. So it gives me area of A plus B minus C, because C is a negative area. It ends up being positive, but that's what we end up with. if I get the area of g of x from 1 to 0 to 1.79, I'm getting the area of b and negative c. So you would get the area of b also minus c. So I'm considering c as a positive area right now on all this stuff. Ultimately, I want to get a. So if we see these two functions, f of x is the same as area of a, area of b, and minus c, to switch that sign, and area of g of x is b minus c, then I realize to get an area of a, because that's all I want, I just have to subtract them. Now I'm going to write this a little bit different, but this is the same thing that we did on the other slide. This will end up being the same thing. So if you look at it this way, we wrote it as two different ones. If we write it this way, we write it as one. That basically gives our area of this. Anytime we got to get area between two curves or area in the x-axis, this is basically anytime we want to find the area between two curves on this one. It works every single time. What my point on that last slide was is it takes care of all these negative areas because you end up just flipping it. So good luck with the worksheets, ask questions.